Hi everyone. I'm just going to show you really quickly how to run your file in R. I'm not going to do every step, but I'm just going to show you what we're working with. Okay, so I'm going to open RStudio. The great thing about RStudio, which is sometimes also a big problem, but is that it starts exactly where you left off last time. So I literally had to clear everything out just to make this video because it had so much old R script. Okay, so I have my script window. This is where you're going to paste in what I gave you. This is going to kind of tell you what's happening, like that thing worked, this thing has 4 characters, all of that. This is where you're going to see plots and packages and whatnot. So I'm going to install ape and Fangorn. Typically you do it like this. These installations might take longer for you because you might not have everything else installed. You already ran this twice today, so I have things installed. Oh, now we're uploading. Okay, so if you were just using R, you would only be looking at this window down here, this bottom 4th lower quadrant. That's why we like RStudio, because we can kind of see everything all at the same time. Okay, I'm going to open the Notepad log that I made you. So you see, this is just text. That's it. There's nothing magical happening in Notepad. But if I copy this, Control-C, Control-V, and paste it into the script, suddenly things are colors. Green means it's just a comment. This is me telling you things, so you should read those. These are commands, and then everything else is like what to do. Okay, so the way this script works is you can highlight and then hit run. And those things happen down below here. In fact, I can run the whole file and it'll all work. You could just run it all at the same time. We're not going to do that because I want to show you some things. Okay, the next 2 steps are really misleading because this is actually hard and is part of the hardest step in using R period. But we made it easy for you because our data set we're going to use, this is where we're telling it where to find that data set. This is telling it what the data is. We're going to call it the file primates. We're going to find it here. It's DNA. It's in the interleaved format. Run. So that took no time. And here it is. And there's 14 taxa, some of which are outgroups. There's a bunch of other junk information in there too. That's what we have. Okay, if this was your file, you would have to change things here and here. This is just an example file from the Fangorn package. Here. You can read all about it in this manual. Okay. So we did that. And then as you're going through, here we're going to build the character matrix. You remember, if you've watched my video already, this takes forever in real life, but it's not hard in with the use of a computer. Here's the matrix. We'll build our first phylogeny. Well, this isn't really a phylogeny. A neighbor joining tree is just how similar the data is you plopped in there. Nothing about evolutionary history. And then we're going to look at that phylogeny. And we made our parsimony one and our neighbor joining one, and we can see differences and similarities. You can expand these and they will adjust so that you can actually read stuff, but let's not deal with that right this second. And then you're going to run scores, and then you're going to get into maximum likelihood. So the good thing about maximum likelihood is it is based off of evolutionary history. It also takes some big leaps so that you can look at more data. Because a parsimony tree looks at every possible change, and then it says this is the way you could get to this data based on the simplest model. Okay? The simplest and fewest number of changes. Now, the fewest number of changes isn't always true. Sometimes evolution's super complicated and you have a loss and a gain and a loss and a gain and a loss and a gain and a loss and a gain, which comes out to one in parsimony would look like one gain, but in real life was a million different changes. Okay, likelihood isn't my favorite, but it is more useful because we can run big data sets. I want to show you something that we are going to skip over for now, but that you might use later. When you're running likelihood or Bayesian analysis, you will have to talk about models. Really, in parsimony, you have a model too. Oh, that didn't work. Coming in. Okay, in parsimony, you have a model too, but you just don't know about it. Okay, this is a very handy little diagram. So we're going to skip the whole model test portion of the PDF. So I would recommend following along in the PDF so you can read about it, but we aren't doing the model test. You're going to just run it for this top model, the likelihood tree for the simplest model, because it's an example. It's a example data set anyway, and we don't have enough time to run a more complex one right this second. But once we started working with DNA, we knew something about how DNA changed. Sometimes a change from an A to a T is more likely than A to a C or something like that. So that's what this weird diagram is. Jukes Cantor, which is the model you're going to use, has equal base pairs. So there should be an equal number of A's, C's, T's, and G's. And actually we can measure that. Now in real life, that's not true. In real life, there's unequal base pair frequencies. There's multiple types of substitutions. And so here we're adding substitutions. Here we're adding different ratios of base pair frequencies with substitutions. And that's what gets you to GTR plus G. The most commonly used model, period. Very seldom is our data not GTR plus G, but sometimes it isn't. Okay, so this is available to you on Blackboard. You don't need this, but just in case, or you don't need this for this project, but in case you needed it for something else, it's there. So you'll see we tell it that just to use this Jukes Cantor, that's what's happening there. You could run a model test. That is actually super easy. I skipped something. I did. It's actually super easy to run a model test, and I can always help you do that if you're wanting to make a real tree. But for these purposes, we're just gonna skip it. You'll see here when it loaded in the base pairs, it said, oh yeah, they're equal. Okay. And then did we bootstrap already? No. And then we're going to bootstrap. I'll talk more about this in a second. Oh, I'll talk more about it now while it's running. So, maximum likelihood makes one tree. And then it tells you how well your data fit this one tree. And this tree searching, hang on, let me show you. I want to make a visual. Okay, so it looks something like this. Uh-oh. So imagine that you have an explorer. Your explorer is going into an unknown territory and looking for the perfect phylogeny for your data set. So it starts randomly somewhere. Here in this, on this blue line, and then it's like, oh, if I swap this thing, then it gets better, but if I swap this thing, it goes down. So every time maximum likelihood is making a tree, it's being dropped somewhere into space and then it's wiggling around to see what gets better. This is why Bayes is sometimes a better option, because Bayes drops a bajillion different explorers. They walk around, they make different decisions, and then they compare all of their findings together. Maximum likelihood, you're going to get one tree. Now, most of the time this is okay, and people with really big data sets are big on likelihood because it is the one that uses the least, that can run the fastest. Oops. Okay. So we made our maximum likelihood tree. Here it is. If we wanted to make it bigger, let's see. Oh, look, that's beautiful. And then these branch links are the support. So when it dropped in and it made that tree, it walked around looking for the best possible tree, and then you bootstrapped it. So then you took that tree and you put through a million fake data sets at it. So if your data set, if you redrew your data set 100 times or 1,000 times, how often would it fit this tree? And that's what these values are. So 85% of the time, human and chimp are the most share a common ancestor, most recent common ancestor. Then next, gorilla. Then next, orangutan. Okay? But look, if we do that again, make a new tree. We look at that tree, 88 this time. It's going to be a different number. So maximum likelihood, while it tells you how support and know that topology didn't change, the support value may change, okay? Bayes takes 1 million of these trees and combines them. So you can be super, I mean, and it can be even more than 1 million. You could take 10 million trees and combine them. So you can be super confident, if I did this all over again, I would get the same result again, okay? So that's what you're going to do. You're going to run that maximum likelihood twice. Okay, so going to your assignment. Installing our, oops, sorry. Okay, it's not the prettiest. I'll put maybe images in later. The PDF is here. This is the exact same thing. All I did is take this stuff out and dump it into a log file so you didn't have to. but it talks